はい。では続いて、東京大学のぐさんで、特定の、eHMI 向けカスタマイズ LLM の訓練ということで、ご発表の方お願いいたします。
So, can you hear me?
Yes.
Yeah, so my presentation will be in English. I hope it will be fine for most of the audience. Yeah,
Okay,
right.
yes, of course.
Right. So, yeah, hello. My name is Gui, and I am the
Mhm.
project assistant professor at the User Interface Research Group. So I think I am the HCI researcher, which is the human-computer interaction, and my work focus on the designing and evaluating the human-centered interactive system. So what is my interactive system? It is the Mm, autonomous vehicle. So my research focus on how the autonomous vehicle communicate with pedestrians, because the autonomous vehicle, like human drivers and pedestrians, often cannot understand their intentions. So to address these challenges, the researchers have proposed eHMI, which is the external interface. So for example, you can see the eyes here on the car. And when the eyes look at the people, then the people will know that maybe the car's sensing system already detect me, then I will feel more safety. So it will be the way to communicate the vehicle's intent through those kind of visual actions. And in my past research, I explored different forms of the communicative robotic eHMIs. So for example, I investigate these robotic eyes on the autonomous vehicle and the expressive head and the arms on the delivery robot. So you can think what I'm doing is the robotic action planning, but it is kind of different, the object different from the traditional robot control. So the traditional robot typically focus on the task completion, such as the navigation and the object manipulation. But in contrast, my research focus more on the communication. So my goal is not only make the robot act, but also make their intentions understandable to people. So for my research, the evaluation of the social effectiveness is one of the most important metrics. And between 2021 to 2024, I mainly designed the eHMI actions manually, so which is the rule-based design. However, the real-world interactions are very highly dynamic in making the predefined behavior difficult to scale. So I reached my bottleneck of the because of those kind of limitation. And at this section, the emergence of the foundation model, the LLM, provide new opportunities. So since 2025, I've been exploring how to use the large language models and vision language models to enable more adaptive pedestrian to vehicle communication. And then it's introduced to this research project. So for this project, it's supported by the supercomputer resource we applied last year, and we finished by this year, January, and we submitted. And also now it's accepted to the ACL 2026 main track, and it will be present in the USA this year. So let me introduce about the related work. So since the LLM-based eHMI design is typically generate the actions and rely on the human evaluation. However, there are three limitations. So it's strong dependent on the prompting and expensive human evaluation and lack of feedback for the self-improvement. So we are thinking that is there any automatic way for the model to improve themselves? And our answer is to let the LLM design the eHMI action, then use the VLM to evaluate them, and allow the LLM designers to refine its actions based on the VLM's perceptual feedback. And this led to our research question that how can we improve the designers, the LLM designers using the VLM feedback. To address this, we introduced an automatic feedback mechanisms. So these mechanisms consist about several sections, and to realize this closed-loop framework, we solve several challenges. So first, we need a VLM evaluation method, And second, we need a collection of scenario for the LLM to generate the behaviors. And third, we need a efficient optimization strategy to allow the LLM designer to really improve its performance. So here is the system overview. We first developed the action database to identify the format for the large-scale fine-tuning. And we let the LLM design the eHMI actions, and we use the Blender pipeline to rendering its action into the video clip. We then ask the VLM to watch the video clip and to give the evaluation result. Finally, we use the VLM evaluation result to fine-tuning the LLM's design. And we will explain them one by one. So firstly, it is the scenario action database. And we first generate the scenario and action database to systematically cover diverse traffic communication context. So why we need it? It serves as the test-based scenario pool, and we will use it as the base for the later development. And for each scenario, we use three type of the LLMs to generate intended message that explicitly reflect the scene's context. It produced 20,732 scenario message pairs. And this dataset contains a broad range of the traffic communicative intent. We then start the context-based rendering. And this is the Blender-based, and we ask the LLM to generate the actions, and we use the Blender to rendering the action into the video clip. We developed this pipeline to support various camera direction and camera distance, and these produce clips from the receiver's perspective, allowing the same actions to be evaluated under different special conditions. So we show some of the rendered demos. For example, here, the scenario and message pair is, the scenario is the autonomous vehicle, the autonomous taxi to pick up the people, and the message is, okay, where you stand, I cannot park, so we need to go a little bit forward. So here is the eHMI is the arm on the car, and the motion is generated by the LLM, and the rendering based on our pipeline. And we also have other examples. For example, here, there is the eyes on the robot to show the information like I'm stuck, please help me. And we also have other example. We use the, here is the light bar. So if you see that light here, it shows the scenario and message pair is want to deliver the goods to the correct people. So here we finish the data collection and data generation. Then we ask the VLM to rate the rendered result. So how the VLM to rate the generated actions. To mimic human perceptions, we design a two-phase evaluation based on the prior HCI research on the eHMIs. The framework consists of 6 evaluation metrics. In the phase 1, the VLM is not given the intent communicative message, and we ask it to rate the targeting score, the certainty, the similarity, and trust. And in the phase 2, we tell the VLM what is the intended message, and we ask the VLM to evaluate the user acceptance and consistency. Finally, we combine these metrics into the single kernel score, which is used for the later feedback and the evaluation. So then, which is the most important part, so the fine-tuning for the auto improvement progress, it contains 1 SFT and 3 DPO. So in the step 1, we conduct the SFT for format-aware fine-tuning. So it is a common practice to give the correct data format for the later improvement. Then we conduct the DPO, which is the iterative preference fine-tuning to align the LLM designer with the perceptual judgment of the VLM. We try 2 methods to improve the diversity of the candidate action. The first is to find the score for the importance sampling. So if the data satisfy these criteria, we then expand its diversity. The second is the diverse bin search, which is the common practice, and we use it for comparison. So after that, we construct the preference pairs by selecting the highest score and lowest score action. So these preference pairs are then used for the DPO training. We repeat this optimization process for 3 iterations. So then here we finish the implementation and the fine-tuning. We will report our results in 3 aspects. So the first is, does our model really align with the VLM preference, which is, does it really learn from the VLM rating? And our trick for the improving diversity really work. And also we do 3-round improvement, which is the 3-round learning. So we want to see whether it can learn step by step, so it become better step by step. And first, does our fine-tuned model align with VLM preference? The answer is yes. So if you only need to see the kernel score, which is the overall performance, the result shows that the progress of the development, the kernel score increase, and the our method is here, and the alignment is also increased. And this improvement is from our DPO iteration, not from the format SFT stage. So just recall that we do 4 fine-tuning. The first is SFT, which is only for the format correction. And the most important step is in the DPO stage. And for the second part, so we have 2 methods to improve the diversity. The result shows that both methods are effective. So if you see, we do the between subject analysis, we try both of the methods, and the result shows that both methods are useful. And due to this efficient sampling, we reduce the training time to around 1/4 without compromising the performance. So we can reach the good performance, also reduce the training time. And for the third part, we compare the result in each round of the iteration by comparing 2 metrics. The first is the kernel score, and the second is the format error rate. So the kernel score is higher the better, and the format error rate is lower the better. And the kernel score is the performance, and the format error score is to see whether it generates the wrong format of the data, because the wrong format of the data cannot be directly used to actuate the robot moving. And to see the kernel score, we find for our 3 types of the eHMI, just I showed before, the light bars, eyes, and arms, from the very, very beginning, so is the early stage, SFT and round 1 DPO, round 2 DPO, round 3 DPOs. So from the very beginning to the round 3, the results all have improvement. So you can see it becomes higher. And if you're looking into the format error, so one unexpected finding was that the light bar shows the higher format error rate after optimization. So we believe it is because the action representation we design may not be well suitable for the expressiveness characteristic of this modality, which means it highlights the importance of the output format design in self-improving system. And to summary, so we develop a self-improving framework consists of 1 SFT stage for output format correction, followed by 3 rounds of DPO training that enable the LLM designer to improve itself using VLM feedback. And our results demonstrate that we answered our research question that iterative VLM feedback can really improve the LLM eHMI design. So here is we have the question for the technical stuff regarding to the supercomputer resource. During the project, if you remember that we do 2 steps. The first is the large-scale generation, and the second is the large-scale evaluation. So for the generation part, we would like to use a Docker for Blender-based video rendering. However, it seems that we do not have the required permission to run Docker. So if there is any documentation or guideline of how to use it, it will be helpful. And something else is we looking ahead. So I believe the foundation model creating new opportunities for HCI researchers is also can for other research. So in the past, there are many research questions were difficult or cannot to explore because the large-scale experiments were very expensive and data collection is time-consuming, and also training specialized model required a significant resource. Today, the foundation model make many of these directions feasible. So instead of building system from the sketch, we can leverage the pre-trained model and adapt them to specific research problem with only relative limited data. So it can be useful for many of the cases. So as a result, researchers can iterate more quickly between the ideas, system, prototype, and evaluation, and to investigate questions that were previously difficult to study. So for me, it is the next frontier of the HCI research. So we can use the AI not only to build smarter systems, but also help us to explore and understand the human-centered interaction in ways that were previously inaccessible, but now we can do it. Yeah, thank you.